as it sweeps across this huge range. So I'm going to sweep from 1,000 hertz all the way up to 70,000. Okay?
我们一般做实验就是这边接一个，那边接个，都会记录下来，再把它全部画出来。他说不要，我从1000给你换一个多的期望，我直接帮你做出来，一次把它做好。但是你们可以试用一下看看。
Of the sweep. The purpose of the sweep is so that I can send all these different frequencies at my circuit and see if that changes the way it behaves, right? And students know that resistors, that doesn't really change. If it's just a resistor in the circuit, it's going to behave that way no matter what the frequency is, right? Or at least at normal frequencies that we're normally dealing with, 1,000 hertz to 100,000 hertz, right? And LRC circuit, we're kind of exploring how does it change, right? How does it respond to different frequencies? And we know that it's going to start changing its shape and its form as it moves across these different frequencies, right? So we're going to send it across that range over a time period of 25 seconds, and we're going to have it step in 1 hertz increments. And you have full control of each one of these things. You know, what you want the voltage to be, how fast you want it to go. Okay? So beside that, I'm going to go ahead and open up the scope. All right, and I'm going to put 2 things in my oscilloscope. I'm going to put the voltage from channel A and the voltage from channel B. Okay? And I'll go ahead and hide that signal generator window because I know it's going to be hard to see the scope. So there's my scope. Okay? Now, Capstone has one other neat thing that it's trying to do for you, and that's try to keep your sample rate tied to your actual time window that you're looking at in your oscilloscope. Right? So what I'm going to do is I'm going to start changing my time range so I know that the frequency response that I want to look at, I know what period I'm wanting to look at, and that might be something you have your students to calculate ahead of time. But I already know in this case, I want it to be a very small time window, right? So I'm going to just kind of drag the time axis of my oscilloscope. And notice as I'm doing this, I don't know if you can see that, but down here in my sample rate, watch that change as I drag my time window. So as I'm dragging that time window, the software is saying, oh, you need to sample faster, right? You need to sample faster to look at all the data points in that time window. So I'm going to keep dragging that out. Yes, I'm taking data more and more quickly as I'm shortening that time window. So I'm going to keep dragging that out until I'm sampling at approximately 5 megahertz. Okay? And you can ask me why 5 megahertz, and I'd say because that's what I told you to do. But you could say, why 5 megahertz? And that's because I've already done the calculations. I know roughly what the response times and my phase frequencies are for these components, right? But your students might not know that. So they might begin with this very big time window and they don't see anything. And so they zoom in closer, and they do it again, and they zoom in closer, and they do it again, until they're finally able to start seeing these responses that they're expecting.
我们做实验呢是 megahertz 是100万很大，所以你看他下面把时间给拉的很小的时间给你去看，但是他常讲学生有时候不太清楚，这个时间不知道怎么办弄不清楚，所以他现在做给你看。
Right. So 5 megahertz, that is a lot of data points, right? And I don't want my software, really choking down on the memory or slowing down based on whatever computer it's using. So I'm going to change the sampling mode in this case. I'm going to say, you know what, we're sampling so fast, I'm not worried about saving every single of these data points. I'm only concerned with saving the data points that are currently in visibility inside of my oscilloscope. So we have a different sampling mode, and that's called fast monitor mode. And that means it's allowing itself to sample at a higher sampling rate without bogging down the software, without bogging down anything, but it keeps everything visible in the current frame of your oscilloscope. So that data is going to stay in storage no matter what you do later in the software. Okay. All right. So let's go ahead and start monitoring that voltage there. So you can see right now I'm flatlined at 0. Okay. And let's go ahead and turn on our signal generator. And I'm going to go ahead and drop that out. Automatically scale that for us. Right, and after 25 seconds it stops. Okay. Now that was 25 seconds going from 1,000 hertz to 70,000 hertz. Maybe you didn't catch what was going on, so I'm going to do it one more time. Okay, kind of watch what's going on. Anybody want to give me some explanation? Anybody want to try to explain what I'm seeing here? So I have two different voltages, right? So I see these two different waves, and at the beginning they don't look like they're anywhere near each other. They look like they're completely different frequencies. But what happens is those waves start changing, right? And they start lining up to each other. And as they're lining up to each other, the amplitude increases. So there's this one point in the plot where I have completely in-synced wave frequencies at maximum amplitudes. But as soon as that starts going, what starts happening? The amplitude starts coming back down again, right? So as we start to understand what happens in LRC circuits, we understand that there's this concept where we have this resonant frequency, right? There's this very key part of LRC behavior where the waves, the frequencies that they are, the circuit is responding changes as I change the signal that's driving it. And this resonant frequency is a key part of understanding what goes on in the circuit. So how do students typically do that? They typically have to say, okay, I want to do it at this voltage, and they take one data point, and this voltage, and then one data point, and then we guesstimate what that resonant frequency is by, plotting and doing like a best fit curve. Well, this one allows students to see exactly what's going on in those circuits as I'm calling across those different frequencies. And not only that, it allows me to stop exactly whenever they're resonating. So I can wait for that moment. So I'll wait for it, wait for it, wait for it. As soon as they're in resonance, as soon as they're at max, I'm going to stop. All right, so I've captured that moment in time where they look like their closest matching resonant frequency and amplitudes are the highs, right? In this case, the red curve is across my resistor. Yep. And the purple curve here is my driving frequency. Okay. Now, why would I stop right there? Why is that so important? Well, I'm going to introduce one other tool here, and that's my fast Fourier transform, my FFT. And I'm going to do an FFT transform on that frequency. Okay? So right now, there's my fast Fourier transform, and notice you can see the range is 0 to approximately 80,000 hertz there. And it's pretty blocky, right? It's hard for me, I can't really tell exactly what this frequency is. It's somewhere between 20 to 40,000 hertz, but I don't really know exactly what it is. I need more detail, okay? So I'm going to go in, and I'm going to zoom in using the number of bins distributed across this fast Fourier transform. So I'm going to say, hey, you know what? I need more bins in my display. All right. So now I have more bins. I can add them to my display and resample that. And notice it just did a live calculation, a live FFT on that data that you just captured in the oscilloscope. So now my students can come in and say, hey, what is that frequency that it thinks is the resonant frequency? There it is, 31,433 hertz. And that's what students have kind of captured as the resonant frequency in the circuit. And that used to be something that was very abstract for students. They rarely got to see, that live transform as I'm calling across those frequencies, right? Especially in the high school level. That would be very hard to do with my traditional data logging. And now I've just done an LR resonant frequency lab in roughly 10-15 minutes, right? So the goal with this, once again, we're trying to simplify the technology so that we're eliminating the barrier of the student understanding the physics, right? That's the core goal, is students understanding the concepts of physics that's going on here without having to be bogged down by the complexity of the software, okay?
这个 RC LC 电路，沟通对沟通是比较难以沟通的。这我们要看一下，我以前是用它的这个课本书本你们要在。LC 电路它有不同的频率，不同的振动方法可以。
Any questions with the LRC circuit? Oh, good. Wow, that's a perfect crowd. What the circuit, like the components of the circuit? Well, I might have them start off, like I said, this isn't the first circuit lab they're going to do. This is the fifth lab they're going to do on circuits, right? They might start off without these other pieces. They might start off right here, just resistors, right? That they might just start off right there, and then then the next one we're going to add the capacitor to that, and see what happens. Right? And then later on, we're going to say, oh, you know what? We're going to add all three of them together. Okay, so this is a fairly advanced topic for beginning physics classes, beginning electronics classes. The phase responses of different LRC components is kind of a up there challenging concept for them to visualize. Right? Now, there's always students who are going to just latch onto the equations and plug away at the numbers, and that's how they're going to learn it. But I'm trying to make it a little bit deeper. I'm trying to enrich that learning by connecting it to the visual things that they can actually see. Okay? Okay, so speaking of connecting abstract concepts to things you can actually see, this next one is probably our most abstract apparatus that we have, and this is our chaos apparatus. Okay?
那下面呢，他说这个电路板哈，其实有很多东西电他都做好了。我有问他，这个电路板比较便宜，比较好做，大家都可以给他注意。那下面他来介绍一个文本chaos， 我跟他做一个分享，各位看一下。
Okay. So I'll go ahead and talk to you a little bit about what we have set up here while we're getting it plugged in. So the chaos apparatus is composed of two sensors. The first one is a rotary motion sensor up here. And rotary motion sensor is used in a lot of different types of labs. It's used in your typical motion card-on-track labs. It can be used to do a linear position, a linear motion. For those of you who are very concerned about accuracy of your acceleration, it can be used to calculate acceleration as the string gets pulled across its grooves. It's used in optics to do our interference and diffraction lab. Okay, and in this case, it's going to be measuring the angular velocity of this aluminum ring up here, this aluminum disc. And this aluminum disc has a point mass attached to the edge of it. Okay?
前面讲的是这个线性的哈，那边做的是一个转动的哈，角位置、角速度等等东西。
Okay, at the bottom down here, I have a photo gate. The photo gate is looking at measuring every time that this mechanical oscillator is driving this arm around. Okay, so there's a power signal, once again coming from the 850, that's driving this oscillator around. Okay, so this is going to kind of push you around here. Alright, and as that's going on, you're going to see these springs, right, move around. Now, traditionally, if I was doing something like this, I'd start off taking off the point mass, right? Unscrew my point mass, and I'd have my students begin exploring that. And that kind of motion, we can kind of fairly understand, right? I can do a couple data runs of that. I get a pretty predictable graph that's generated, right? The same data points are generated every time as I do this. Right? It's a pendulum motion, harmonic motion. That's pretty easy for students to grasp onto. But what happens to pendulums whenever I start making things a little bit weird, right? So I'm going to attach this point mass, and what happens? Well, we introduce a little bit of chaos, right? We start having nonlinear behavior in this system, okay?
他这边讲说，它跟是一个光电门嘛，大家都知道哈。然后它这边是一个旋转盘，但是它现在用个点质量放在这边，特别加强，然后这样做起来可以产生一个 chaos 的情况。我们来看看它怎么做。
Up a chaos lab I have here. Alright, this is also a good time to introduce our workbooks in Capstone. So Capstone's other biggest advantage is it has these pages built into it to kind of guide students through the activity. So in this one, students are going to kind of walk through the whole introduction, the setup, and everything inside of Capstone. So, traditionally I would have like a paper printout. I have some other lab manual I expect students to always have with them as I go through. Well, I've taken a lot of that information and I've included it in the software. All right, so students have access to that information right beside where they're going to be doing their data collection. Okay, so I have a little bit of introduction here about what oscillators do. And then I have a nice little introduction to the theory of chaotic motion. And this breaks down kind of the same stuff I was just talking to you about.
他做得很棒啊！他说他把所有东西可以做到这里面去开始就是介绍学生做实验都可以介绍说明都在这里面。我也想说这很棒，我也不要再给学生看那么多记录那么多东西，就整个给你介绍，就丢给你，他全部跟你做好了。然后你看刚刚在当漏一大堆东西他已经事先在美国都做好，然后给学生做一系列这个系统。
So this page tells you just some of the stuff that you can graph to look at the behavior of your chaotic motion. Obviously, the most basic one is angular velocity versus time. So you're looking to see how the angular velocity responds to this motion. The second one is what we call phase space, right? And phase space is angular velocity versus angle, right? Angle of rotation. So I can see how the angle velocity is changing at different points of the rotation around the disk, right? And finally, we have what we call the Poincare plot. And the Poincare plot is kind of the most advanced thing they're going to get to in this type of activity. And it's basically phase space, but taking one plot per phase. All right? So we're going to take a plot of the angular velocity versus the angular position, and we're going to do that once every time that the photo gate is triggered. Right? So that's why that photo gate's there, is to tell it, oh, that's one rotation. Oh, that's one rotation. Okay?
它是用那个 photo gate 这边来驱动它那个角位置，还有角速度angular velocity 在那边参数在做到记住了这些动作，都把它记下来。
Okay. Another extension that you can do this activity is calculate once again the potential kinetic energies that go on in the system. So I can calculate the potential well of the oscillator. Okay. And I'm not going to walk through those today. You can see that in part of this experiment. I have my setup instructions, so this actually tells the students, how to actually connect everything that I have going on here, my strain, my masses, the sensor. Notice this is another nice tool about Capstone. I can integrate my photos directly beside my text and instructions. All right, this page is designed to calculate your potential wells. I'm going to kind of skip over that one for the sake of speed here. Okay, and here's two plots I have already recorded. Now this is an experiment that you typically have to record lots of data points for. And this data was collected over approximately 2 hours. So I obviously don't have 2 hours to sit here and wait for you to run through this plot. But I'm going to use kind of the tools of Capstone to kind of show you what this plot looks like and how it's created in real time. So I'm going to use those playback tools you just saw earlier, and we're going to play back some of this motion. All right, so there's the plot. Let's pause that for a second. So you might be wondering what is going on here, what's creating that motion. So I'm going to go ahead and start up my signal generator just to show you what's going on here. So we're going to drive this guy. So let's go ahead. As you can see, our arm is starting to move there. All right, so I can adjust my DC voltage. I can speed it up, I can slow it down. So typically, as I'm setting this experiment up, I would have my students go ahead and monitor these different pieces to kind of start figuring out what the right signal is, what's the right voltage for me to be driving my motor to create the chaotic motion. All right? And I also have, one thing that I skipped earlier, I also have a little magnet mounted. You'll have to kind of, I can't really rotate it around here. I have a magnet here, and I'm sorry I skipped over that earlier. So that magnet's actually creating a damping force on the disc, and that's why it's important to be an aluminum disc. So that's also a very important part of introducing the chaos here, is students can adjust the distance of this magnet to the disc and control the amount of damping going on this disc. All right.
跟你就是阻尼我们课本里面讲的，它练后面就是里面有地方控制它。
Okay. All right. So anyway, so that's what it looks like when it's in motion. Here's my data again. So as you can see over time, I can kind of take a look at what's going on. The top graph, by the way, is angle versus time. So you can see what the angle is doing, where the position is of the sensors that's going around. Okay? The bottom one down here is the angular velocity versus the angle, and that's with the damping turned on. Okay? Stop it. Thank you very much. Sometimes chaos takes a little bit of a push to get things going chaotic. Alright, so students would get this running. Like I said, they'd be running this for a long period of time. They'd be running the chaotic motion. And obviously you need to tweak the length of your strings, you tweak the driving voltage of your mechanical oscillator so that you have continuous chaotic motion. My setup here, there's a couple of things I still need to tweak, as you can tell. But this is the clock that I'm aiming for. This is what my data should look like once I get things going chaotically. And finally, the point here plot. Turn off my driver for a minute. So there it is, non-chaotic. I see a very repeated pattern. And let's go ahead and take a look at what our chaotic motion looks like. So this is our point here plot. Let's take a look at that. So this is the one that's taking that one point every time that photo gate is passing through the oscillator, and it's taking this point for the velocity and the angle. Now, obviously, that's a lot of data points, and that's why you have to run it for long periods of time, because you're trying to generate a lot of different amounts of data. And what you'll start seeing here is that it never quite repeats the same path, right? If you're following it, kind of generate the path as it goes from one quadrant of the positive angle rotation to the negative angle rotation in the opposite direction, we see that things are never repeated. These paths never draw over themselves, right? And that's kind of the key of the point-Gaire plot. Now there's another nice thing that the software is doing here for us, and it's changing the transparency of each one of these plots. So you'll start noticing as I have the more closer motion, the closer points repeating the pattern, you'll start seeing spots get darker. Right? So you see how some parts are getting darker than other spots? All right, that's because this velocity versus position is happening more frequently at those parameters than it is at other parameters. Okay, and I'll kind of point that out with my mouse here. So notice you start seeing these darker ridges on the edges here. You see some darker ridges over here, but you see very light color patterns here, right? Very, very less common repetitions there. So at these larger angles, you typically see these lower speeds. Things are slowing down as those angle transitions get so big. And as those angles start approaching zero, right, it's very rarely going to be the same speed, right? It could be going very fast or very, very low. Okay? So that's my chaotic plot. Very, very abstract concept. Very hard thing for students to visually grasp and actually collect data on. So this is an attempt at taking this higher level concept and once again turn it into something that students can easily see. All right. For the sake of time, I'm going to have to move on. I have one more that we're going to try to show you today, and that's our bridge, which is looking a little tipsy. All right. So let's see if we can get our bridge set up. We're going to kind of do that one. Now wrap up our session. Are we going to move it over here? Yes. This poor bridge has been moved around a lot today, so it's taken a bit of a beating. I'll give you a quick introduction. This is the Pasco structure system. The structure system was designed about 2 years ago, specifically targeting structural engineering programs. So this is core component system that consists of just simple screws and I-beams. These are just screws and I-beams that can be used to build a wide variety of different devices. And this is one of the larger types of systems that we make. This is a suspended string bridge, suspended rope bridge, all right? Cable bridge as it would be in reality, right? This is where we use some strings. All right? And attached to the, yeah, it's taking a beating today. It's a little, but I think it'll still get the point across. So, attached to this bridge, and what makes this system so much different than what you typically have in your structural engineering program are these sensors. So I have these stress strain sensors at these even intervals across the bottom of my bridge here. Okay, and those are just looking at what the stress and the strain is across a simple strain gauge, right? Strain gauge? Is that strain gauge?
这就是我们工程里面用strain，就是应变应力，好，知道好，这个就用在这个地方来测试，它做给你看。
Alright.
对，它有 sensor， 它有很多的感应器在这个地方，它这个就是感应器进行做。gauge 可以的，因为我不是工程方面。
Okay. So I have a static mass suspended from one side of those strain gauges, all right? And then what I hope to do is I hope to kind of drive my little vibrator. This is going to be my earthquake, right? This is going to be my natural disaster.
这人造的地震哈。
Right? So as I start vibrating and as my earthquake gets worse, it's going to start oscillating this bridge, right? And we all know whenever systems get this big, most people think that this is you drive over a bridge this large and there's hundreds of cars, it's built out of steel, people think it doesn't move, right? They think it's completely always steel and stable, just like Taipei 101, right? People see that and they think, oh, it's fixed, it never will move. That's not true, right? We all know that these mechanic systems, they have just like a ball on the floor, just like me standing here, we're all susceptible to these vibrating frequencies.
他是讲说这个桥上很多车子一大堆动力放在大家都认为那个桥很坚固，其实不是这样子的。他站在这个建筑会有生物坚固哈，他电人讲给你听，做给你看。
Now I might question the structural engineer program that this civil engineer graduated from, because things are a little off here, but I think it's going to get our point across. Okay? So we're going to start off just looking at a simple graph. All right? We're good? Okay? All right? So in my graph, I'm going to look at just measuring force. And I'm going to start off with just one of these forces. And I'm assuming this is 1, this is 1, this is 1, 2, 3, 4, 5, 6. So you can see I have a list of force sensors to choose from here. I have 6 different force sensors. So we're going to start off just looking at the first one. I'm going to increase my sample rate on it. All right, and once again, we're going to use that signal generator to drive it. All right, now let's start off at a fairly low frequency and a low voltage. All right, so there's a very low frequency, a very low voltage. And notice that the bridge has got enough mass that it doesn't really show you much vibration going on at that level.
他现在是用第一个感应器做给你看，用5赫兹做给你看。
All right, we can increase that. And there's 2 volts, 3 volts. Okay, basically this is increasing the magnitude of that earthquake. 5 volts.
振幅啊 ，amplitude 振幅应该50克吧，好，我们看看清楚。
Notice at 6 volts, we start to see a little bit of vibration, right? Masses are starting to move, roads starting to flex a little bit. 7, 8 volts. 8 volts, you can really start seeing the whole thing starting to move, right? So all we're doing is simulating an increase in that earthquake, right? We're making stronger and stronger earthquakes. This would be a fairly large earthquake. This is causing this structure to move a bit. Okay, so I'm going to go ahead and leave that running. And while I leave that running, let's go ahead and start recording some data. So there's my graph of my force, and I can go ahead and zoom in on it a little bit so you can see what's going on there. Let's go ahead and stop that. So you see tiny vibrations. Right? All these little masses are moving. Right? Now that's just one. That's just the vibrations of this one. We can go and look at the different vibrations all together. So let's go ahead and add another one to this. Alright, so we're going to go ahead and add force number 2 to this.